Okay, so we learned a couple different types of spectroscopy in these two units, chapter 14 and chapter 15. So, right, just to be clear, we're doing two chapters, 14 and 15. The first thing we learned about, the first type of spectroscopy we learned about was mass spec, right? It was mass spec. And what happens in a mass spec? There's an electron beam. So there's an electron beam, hits molecule, knocks out one electron, and also subsequently breaks up, right? Subsequently bonds break. Bonds break. Right? Hit basically, this is a destructive thing, right? You hit a molecule with an electron beam, you knock out one electron, the molecule starts falling apart, right? It all starts breaking down. Couple terms, when you lost just one electron, what was that called? What was the molecular ion? Molecular ions just lost one electron. The most, right, if you're going to form fragments, if you're going to break bonds, what kind of fragments do you expect to make? The most stable, right? You're always going to form a radical and a cation, but you always want to form stable fragments. In particular, you're always going to find what kind of fragments? Positive fragments, right? Those are the ones we detect. Stable positive fragments. Right, you always have one part of the fragment has a plus charge, one's the radical side. You always want to form stable positive fragments.
What would the neutral fragment? Is that
So the neutral fragment is the radical. The radical is a neutral fragment, right? There's no charge on that. So radical is a neutral fragment. So let's just give an example here. We're going to break a bond. So let's say we form the radical cation, right? We knocked one electron out. So we knocked one electron out. If we don't have heteroatoms, we don't know where the electron got knocked out, right? If we have lone pairs, right, it's usually easiest to knock the electron out of the lone pair. But if a molecule like this doesn't have lone pairs, it's kind of hard to say where the electron got knocked out. So you do a little dot plus up here. But now, if this is going to keep breaking up, what kind of fragments do I want to form? I want to form stable fragments, right? So let's say I break this bond, right? Now I have a choice. Where do I want to put my plus charge and where do I want to put my radical, my dot? We're trying to form stable, positively charged fragments. Which one of these is going to be the most stable if it's positive? Is it going to be A or B? A, absolutely.
why?
Good question. Not conjugation. Hyperconjugation, right? Remember hyperconjugation. It's a tertiary carbocation. So the other side is a dot radical, right? That's what the dot's at. Remember, hyperconjugation is when you have a carbocation, which of course is sp2 hybridized. That's empty. And adjacent to it, you have those hyperconjugation buddies. Oh, this one would say CH3. Right? That's where these electrons in these bonds that are two bonds away from the positively charged carbocation, 2 bonds away, right? They can help stabilize this empty orbital. These electrons in the bond, these sigma bonds, can stabilize the empty p orbital. And the more sigma bonds you have 2 bonds away, the better. So in tertiary carbocations, how many sigma bonds are 2 bonds away? How many are in this carbon right here? 3. How many are in this carbon? How many are in this carbon? Right, so tertiary carbocations have 9 hyperconjugation buddies, which makes it very, very stable. The more hyperconjugation, the better. Right? So we're always trying to form tertiary carbocations if we can. Now, we could have also broken the bond here or here or here, got tertiary carbocations too. Right? There's more than one way. So the most stable fragment piece we call the base peak, right? The biggest peak the peak that's most abundant, right, the largest peak, that's the base peak. That tells you that's the most stable fragment. That's the base peak.
So a question like this, do you want us to write all the possible, like,
I wouldn't, I mean, if I asked for all the possible, but I don't think I will.
so you just want like one?
I would ask you for the most stable fragment.
And that can be more than one answer.
Sure.
Yeah, okay.
Right. Absolutely. It could be more than one answer here. Absolutely. But the why is the same, hyperconjugation, stabilization, right? This idea of this empty, this bond, these electrons here, moving and helping stabilize that empty p orbital. Hyperconjugation. sp2 hybridized, sp3 hybridized, right? So it's not perfect. It's not perfectly lined up, right? Because this is still 109.5 and this is, right, 90 here. So it's not perfect, but it's better than nothing.
It's a tertiary carbocation.
This is a tertiary carbocation here. Yep, what I have drawn. Yep. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9 hyperconjugation buddies. And of course, what does it actually tell you? Right, the molecular ion here, right? It tells you the mass. Mass. Right. And the fragments obviously give you a mass as well. So it helps you understand where the molecule breaks up. So to demonstrate some mass spec type of problems, this is 12 from 2013 exam number 2. And it shows you this bromine. Lone pairs on the bromine, of course. It says electron beam. So what happens first in that first electron beam? Knocks an electron out of where? Bromines, lone pairs, right? So we're going to knock an electron out. See ya. And here it also asks you to draw the product of this twice, so let's do that. So we're going to draw this twice as it asks us to, because we're going to show two different ways this fragment, two different routes this fragment can go down. So it's more helpful to just draw it twice and try to draw arrows over each other. All right, so we draw the same thing. These are the same. And in one part, we asked to do alpha cleavage. Actually, do two draw arrows for one. So we give you the product of two different alpha cleavages. So remember what an alpha cleavage is when you break the bond between the alpha and the beta carbon. Right? So here, whatever carbon's attached to the thing that lost an electron, that is considered the alpha carbon. So this is the alpha carbon. That would make this a beta carbon and this a beta carbon. So there's the alpha carbon. The thing attached to the alpha carbon are the beta carbons. All right. The way alpha cleavage works, right? You're going to break that bond, right? To break that bond between the alpha and the beta carbons. So if I just draw one direction here, I'm just going to draw the electrons in between that alpha and the beta bond. Because that's the bond I'm breaking. Right? This bond, so I need to move those electrons. When we do alpha cleavages, these cleavages are homolytic cleavages, moving one electron at a time, meaning we have fishhook arrows. Also, for an alpha cleavage, you should remember you always form a pi bond, right, between the alpha carbon and the bromine or chlorine or oxygen. And the other electron goes to the beta carbon. So there's one of the electrons there, right? This is our beta carbon. And what we have left, we didn't do anything over here. We formed a new pi bond, right, with one electron, two electrons in a bond. Bromine still has two lone pairs. And now where's the plus charge? Still on the bromine. Yes, good. Right? We could do it the other way as well. Right? We could do an alpha cleavage this way, on that bond right there. But all I asked for was do it one way. Choose one. You can do alpha cleavage either way. Choose one. So that was the homolytic alpha cleavage. The other thing we wanted you to do was say a heterolytic cleavage. Hetero cleavage. Right? That means you move 2 electrons at a time. Right? In this case, we're breaking the bond between the alpha carbon and the bromine. Right? Or in the other case, right, we broke the bond between the alpha and the beta carbon. Now, right, we're going to break that bond between the alpha carbon and the thing that lost electron originally. And we're going to move 2 electrons at a time, double-headed arrow. And so now where does the plus charge end up on? Which carbon? It's actually in the alpha carbon. And the bromine has how many electrons around it now? 7. So why isn't the bromine charged? Because bromine starts out with 7 valence electrons, right? Sure, it wants 8, but it doesn't have a charge if it has 7, right? Bromine has 7 valence electrons. So that's the heterolytic cleavage. Which one do you think is more likely to take place? Do you think right, so this is the alpha cleavage, right, with the homolytic, right, 1 electron at a time, fish hooks. Which one do you think is more likely to take place? Alpha cleavage or heterolytic cleavage? Why? Well, there's 2, so let's just analyze them both, right? Which ones, so look at the differences. Okay, so here we have a plus charge in the Br. Everybody has a full octet. That's a good thing. Here we have no plus charge in the Br. We have a carbocation. Is carbocation a full octet? So that's not good either, though, right?
Bromine doesn't want a positive charge.
So you could argue either, right? So what I'm getting at here is, right, you could say, okay, bromine doesn't want to have a plus charge. I don't think alpha cleavage is going to take place. Perfect. You could say, yeah, but in this one, everybody has a full octet, or at least the bromine has a full octet, or something does. This one has a carbocation, now with a full octet. That might not be great either. You could argue either way, right? It wouldn't be right or wrong. I mean, I think this one is probably less likely, so it's more likely to do this, right? Because the bromine doesn't want to have the plus charge. But if you were thinking about this and looked down there and said, wait a second, this is the carbocation, right, without a full octet versus, right, does this bromine have a full octet? Absolutely. So maybe you say this is better because this has a full octet, this one doesn't. That's a reason. It might not be the most important reason, but it's still a reason. And so unless I gave you the mass spec and showed you the heights of the peaks, you wouldn't necessarily know, right? But you see, you can answer both ways. As long as you have a good reasoning behind either way, it's good. All right, so the next type of spectroscopy we talked about was was IR, or infrared spectroscopy. Whatever. Go pee. Right? What happens in an IR spectroscopy?
No, that's UV.
That's UV. IR, what happens? Right? You shake it up. Right? Shake it up. You can apply pop songs to pretty much everything in chemistry. Right? So in infrared spectroscopy, we hit a molecule with infrared radiation. Right? Infrared radiation. It will shake and vibrate bonds. It doesn't break bonds. Mass spec broke bonds. Just shakes and vibrates them. And different functional groups can be identified by these. Right? Acetyl bond O stretches differently than a CO, single bond, right? All those different things we talked about, how mass affects this. We talked about how triple bond, double bond, single bond, how that affected this, right? Remember Hooke's law, right, which just took into account basically bond length and the mass of the two things, right? So basically every different type of function group has a different type of stretch or bend or all these different things. And that's what we can identify function groups with this. All right? So yeah, they're absorbing the infrared light, infrared radiation. They start shaking and bending, right? And because like function groups are different, right? Right? You can say, right, a classic example was the ester versus the amide. We talked about how resonance can affect things and how induction can affect things, right? All those ideas of how that will affect the frequency and the wave number, right? The shorter the bond, the higher the frequency, the tighter the stretch. So it'll give you a higher wave number, right? Shorter the bond, higher frequency, right? It's going to go, short little bond's going to go like this, quick, right? So it'll be of a higher wave number. Polar bonds do things differently too. So you've understood this, or you've been identifying all of these, right? With your little tables. Remember, so things to think about, how induction affects, how resonance affects it, how the type of bond, I'm saying triple, double, single, how the mass of the elements can affect it, all those things. There's myriads of examples we've given you for all those things to think about how that happens, right? So the one I have here, right, an ester versus an amide. Right, the question is here, what's more likely to happen, resonance or induction, right? Oxygen's more like, right, what's the biggest difference here? They're both carbonyl acetyl bond O's. One has an oxygen off it, one has a nitrogen. What do you guys know? What's the difference between oxygen and nitrogen? Which one's more or less negative? Oxygen, so it's probably less likely to do resonance, right? And resonance, we mean donating electrons in. So for esters, induction is more important. Right, so what does induction do in this case? Just in this case, induction in this case makes this bond shorter, tightens it up. So it's going to increase that wave number, right? It shortens this bond up because we're pulling stuff away. So it shortens this bond up, increases the wave number. Induction doesn't always increase the wave number, but it does in this case. But now in nitrogen, less electronegative, more likely, right, to donate its lone pairs. And that gives us a species like this, right? Where now, because resonance is likely here, this acetyl bond O isn't necessarily always like a double bond. It has some single bond character. And what kind of bond is longer? A single bond or a double bond? Which is longer? Single. So which one's going to have a longer stretch or higher or lower frequency single bond, right? So that's going to, this resonance in this case is going to decrease the wave number. Right? So these esters come at around 1740, and these amides usually around 1680. Right? So you see how it changes the frequency based on, right? Is it giving a single bond character? Is induction important? All those things. Yeah, another factor is hybridization, how that affects. That also kind of goes into the type of bond. But remember, on your tables, there's some numbers, right? If you have an SPCH, that's at around 3,300 and is sharp. SP2s are around where? 3,100. It's always right, 3,100 or so, approximate. And then an SP3CH, those are, right, 2,950. They're never above 3,000. Right? They're never above 3,000. Right? So how does hybridization affect this? Right? So what changed? What changed in these CH bonds as you go from sp to sp2 to sp3? What changed? The bond length, right? Which one's the shorter bond? SPCH. Well, that makes sense, right? Because a shorter bond would have a higher frequency. Higher frequency would mean higher wave numbers. All right? So you can see that showing up here too, right? A short little bond, right? We can really crank on a short little bond, right? Get a higher frequency versus a longer bond.
But how do you decipher it between alkene and the aromatic? Like they're
So,
both-
yeah, aromatic CHs are sp2 CHs too. So they're around the same area, right? So this alkene can be an aromatic ring too, for sure. Any sp2 CH is around this area, above 3,000. Any type of sp2 CH, whether it's an aromatic ring or just an alkene. So you can't, right? Remember IR, it can tell us, it can't give us the whole picture, right? It can tell us we have sp2 CHs. It doesn't tell us this sp2 CH is on a benzene ring or this sp2 CH is on an alkene. It doesn't tell us that. It tells us we have them, but it doesn't tell us exactly what types they are. All right, as we go down our spectroscopy lanes, UV vis. This should be a quicker one. UV vis, we hit a molecule with UV or visible radiation. Right? So mass spec, we broke bonds. IR, we shook up bonds. UV vis, we're not going to break bonds. We're not going to shake bonds up. But if we have pi bonds, we're going to take a pi bond, or at least one pi electron, and make it go to pi star. Right? So we have our pi star. So essentially what we do is we excite one electron. We hit it with some energy. Right? If this is energy. We hit it with some energy, and it goes up to pi star, but then it comes back down. So we don't break any bonds. We just excite one electron. Right? Excite a pi electron. Electron in a pi bond. Right? Excite a pi electron. So UV tells us we must have what? To have a UV vis spectrum. Must have pi bonds, right? We gotta have pi bonds. And in particular, probably conjugated pi bonds, right? Must have pi bonds. Right? Most likely conjugated. Right now, what happens? So we're talking about UV and visible light. Which one's a stronger radiation? Ultraviolet light or visible light? UV is right. So does it have short wavelengths or long wavelengths? UV. UV has short wavelengths or long wavelengths? So if you told me it's higher in energy, right? Everybody's with me on UV. UV is more damaging. So what's a higher energy wavelength? A long wavelength or a short wavelength? Short wavelengths, right? As you get, right, the difference in energy gets longer, you go to visible, right? So what we're measuring is this pi to pi star, right? We're measuring this gap from pi to pi star. If you have a lot of double bonds that are conjugated, the gap between pi to pi star becomes less. So it takes a longer wavelength to make that transition. Right? So I'm just going to give you a concrete example.
So that's a longer wavelength?
Yeah. So I'm just going to do concrete examples. Right? A and B. Which one's more conjugated? A is more conjugated. So A's energy gap should be bigger or smaller from pi to pi star? Should be smaller, right? Smaller energy gap pi to pi star, right? It's going to take less energy to go from pi to pi star with more conjugated double bonds. So if it's a smaller energy gap, is it going to need a long wavelength or a shorter wavelength? Longer. So longer wavelength than B.
A has a longer wavelength?
A has a longer wavelength because A is going to have a smaller energy gap. Longer wavelengths, right? Lower energy, right? Longer wavelengths, lower
Is this
energy.
that lambda max or is that something different?
Lambda max is this.
Okay.
Yep, this is this. right? That's the same the wavelength that it takes to go from pi to pi star,
Okay.
right? So if you have more conjugation, your energy gap between pi to pi star is less. So it takes less energy to go from pi to pi star. So you're going to need a longer wavelength than you would normally. More conjugation, longer wavelength, smaller energy gap. Until you get to the point where you have so much conjugation, then we have color. Then we have the visible spectrum, right? Then you start dipping into that part.
Wait, so much what?
So much conjugation, or so much pi bonds all lined up in order, that it takes, and then it's visible light that goes from pi to pi star. So it's even less energy, even longer wavelengths. All right, for the grand finales. So let's do Hnmr. What is Hnmr? What happens in an Hnmr experiment? Right? Any NMR experiment? We applied magnetic field, applied uniform magnetic field, we'll say. So we line up the protons.
The magnetic field does that?
Yep, lines up the protons in either alpha or beta states. All right, line them up in either alpha or the beta states. So either they're with the magnetic field, the big one, or they're against it, one of two places. All right, so you can look at it like this. Here's the beta. There's the alpha. The big magnetic field that they call B0. All right, is going that way. So either you're going with the magnetic field or you're going against the magnetic field. All right, and again here. All right. So your protons will be in alpha or beta states. You get them all lined up one way or the other, with it or against it. And then what do you do? What do you hit the protons with? You hit them with radio waves. Radio waves. Right? And then you measure as they come back into resonance. So you measure the frequency it takes to knock them down and as they come back up. Right? So actually NMR is actually the least destructive of these spectroscopies we've done. Right? Mass spec, right? You knock an electron on, you start breaking bonds, right? In IR, you actually start shaking the molecule up, right? UV vis, you take an electron and go from pi to pi star. And in an NMR, you just hit it with radio waves. We're getting hit by radio waves right now. Yeah. So it's a very fine difference. And we talked about this a lot too, that we can, right, some protons are very similar. Remember the HD versus standard definition conversation? But our little NMR gave things in standard definition, right? It gave the right frequencies, it gave the right integrations, but it didn't quite give us that fine, detailed picture, right? It's because some protons are very similar. So as your magnet gets bigger, the differences between your alpha and the beta states get bigger as well, right? So you can start to see those fine differences between protons, right? So that's what we're measuring, is those differences between those energy levels. So that's what happens, right? Big magnetic field, get the protons lined up, you hit them with radio waves, you measure what frequency it takes to knock them down to get them to come back up, right? We see these peaks. So what does NMR actually tell us? What are the four things, right? The four things were the number of different H's, right? So that's the number of peaks. It told us something about shielding and deshielding. Shielding and deshielding, right? Is the hydrogen shielding are the H's near electronegative elements, right? Are they upfield or downfield? Of course, if you're deshielded, you're near an electronegative element. If you're deshielded, you're going, right? Deshielded, downfield, right? The third one, they told us something about like what H's are next to or near each other. Right, that's that splitting, that nearest neighbors. Right? Do the H's have the same coupling constant? Are they coupled to each other? Are they 3 bonds away? Right? Can they hear each other singing? And then the last one was, it told us something about the relative ratio of H's to each other. Right, that's at integrals. Relative ratio of H's. Right, that's at integrals we took. And I think you've probably noticed by now, you need all this information to answer some of these tough questions, right? It's not, you really need to think about, right, if I'm next to an oxygen, what will my frequency be versus next to a nitrogen, right? You have to really know those fine details, and that table should help. Right? But that does make a difference, right? Coupling constants help because they know who's talking to who. All those things help. Think about shielding and de-shielding, right? First, you got to figure out how many different types of H's you have, right? Right? Every new peak in the Hnmr represents a new type of H, chemically non-equivalent hydrogen. Those are the 4 things they tell us. It tells us. So a quick one for C13 Hnmr. This one's nice. There's no splitting. Same idea as what happens, but what it tells us as far as like the radio waves and all that kind of good stuff. Same idea, same experiment. Big magnet, uniform field, right? Hit it with a radio wave, measure that frequency. Same idea. This one tells us the number of different carbons, right? So if it has 5 carbon peaks in the Hnmr, the CNMR, you have 5 different types of carbons, right? The frequencies do tell us some stuff, right? The frequencies, the shielding and de-shielding isn't as helpful. De-shielding and shielding is not as helpful as it is with proton Hnmr, right? You could say the C's of the carbonyls, C double bond O's, is always way downfield around 180. But other than that, like the ranges kind of overlap, and it's not that useful. Also, the integrals don't matter. Don't matter. Very sad. Frowny face. Right? Integrals don't matter. You don't integrate carbon-13 Hnmr peaks. Doesn't tell you anything about it. There's a loose interpretation about the size, but it's loose. So it doesn't tell you much about that. So really it just tells you the different number of, right? It's kind of like that check of like an IR would be a check, right? If you've done some of these, right? If you've done these and you say, I get done with my problem and I look at my carbon Hnmr, says I have 4 types of carbons. I better have 4 types of carbons in my product, right? Or just the same way you'd done, like say you've come up with an idea for your final thing and it has an OH, but then you go back and look at your IR and say, there's no OH peak. This can't be right, right? That kind of thing. It's kind of like a check almost. Sometimes if there's very few carbons in a carbon Hnmr, that tells you something about symmetry perhaps, right? Just like if there wasn't very many peaks in an H Hnmr, that would tell you the molecule might be symmetrical as well. But yeah. So this is number 13, 2013 exam number 2. So what do we know? We have C6, H10, O2. So the first thing we always got to do, degrees on saturation, is, all right, so du is equal to 2, which of course means we have 2 pi bonds or rings. There you go. Some combination of them. So the next thing I always like to look at is the IR. So what does the IR tell us? The IR says there's a peak at 3020. There's a peak at 1740. 1654. 1186. And 971. Now, I mean, be careful with these IRs. I mean, I wrote this one, so I gave you all these numbers must have meant something, or should mean something, but some should really stick out, right? So after doing all these problems, hopefully some of these just like scream something at you, right? So 3020, what does that tell you? C double, but it tells you there's C double bond C, but it tells you there's a sp2, what exactly? CH, sp2CH, right? So be careful, right? So don't write, right? So be careful, don't write, right? That stretch tells you sp2CH. right? It does also mean you have probably have an alkene, but this only tells you that. 1740 tells you what? C double bond O.
Wait,
And we don't necessarily know exactly what it is. Let's just say C double bond O.
you missed the 2955.
Which one?
2955 is the IR.
Oh, my bad. Yeah, I did miss. There's also a 2955. So what does 2955 tell you? sp3ch. Alright, sp3ch. Here we go, guys. 1654. What does that tell you? It could tell you C double bond O, but it might mean alkene, right? This is the problem with IR. Right, okay, maybe. Alright, but write a question mark. I'm not sure. Alright? I don't know if that means I have two C double bond O's, maybe, or what, but I'm not overly confident about that one. What about 1186? Anybody got anything for that? A CO stretch? Okay. What about 971? That's the key. Look at your IR tables. There's a whole part of the table there dedicated to C double bond C's, terminal alkenes, cis alkenes, trans alkenes, all dedicated to that. 971 tells you, I heard it, trans. So, maybe the 1654 is a C double bond C. So this tells me this, right? A trans alkene. So what are the two most important pieces I take away from this? At this point, this seems really important. That for sure I know is there. And then this is telling me for sure that's there. So I'm going to do what I always do. I like to subtract out the pieces, right? So you have two pieces there, right? You've created two pieces to the puzzle. Subtract out a CO. So you have C5H10O. Subtract out a C2H2 piece, right? C3H8O. Now I haven't even looked at the Hnmr yet. And I've already got it, right? I've already eliminated 3 carbons of the 6, right? So now let's look at the Hnmr and what it says. It says there's a peak at 6.70 ppm. That is 1H. We're calling it a multiplet. And giving it coupling constants. That's wrong. That's fine. Right? We'll say it has a coupling constant of 1 hertz and 15 hertz. Now that should have been a big ding ding coming off in your head there. Not a ding ding benzene ring. But you see 15 hertz, you only require to know 2 coupling constants, 10 and 15. And 15 hertz coupling constant represents what? Trans alkene. Absolutely. So I should be telling you, oh, that might be that. No, it should not might. It is that.
From 10 to 15 is
10 is cis, 15 is trans. It is a fact. And you can't figure it out without knowing that. It's literally, right, because they'll both be doublets. It's hard to tell. You need to memorize, I've asked you to memorize 2 things. 10 and 15. 10 is cis. And even really you don't need to memorize it because the IR just told you. To be fair. Right? 5.9.
Is that why you put it so it wouldn't throw us off?
Yes.
Okay.
It's nice when different pieces of data confirm the other piece of data, right? It's helpful.
If we didn't see that 15, which most likely we wouldn't have, then would we have doubted that it was going to be a trans?
Don't ever doubt yourself.
Okay.
The IR would have told you it was trans for sure. For sure. All right, 15 or 15.5.9, 1H. It's going to be a doublet. And it has a coupling constant of 15 hertz. Cool. Another one at 4.05 ppm. 2 H's. It's a quartet, Q. The J is equal to 7 hertz. 1.88 ppm. 3 H's, doublet. J is equal to 1 hertz. 1.21 ppm. 3H, a triplet, and J is equal to 7 hertz. All right. So what I like to do at this point, right? How many different types of protons do we have?
5.
Right. So I write here 5 types. You write that. I'll write next to it +1.
Are you ever going to ask the question that's harder than this one?
I don't know. Don't you want me to? Am I going to ask you a question harder than this one? Now I feel compelled to. Right? Okay, so there's 5 types. And so I announce that there's 5 types. And then I write here, I'm going to call this one A, this one B, that C, D, and E, okay? I already have 2 pieces. Right? One of these pieces contains hydrogens already, so I want to make sure I don't re-subtract those out. Which 2 H's are represented in this transalkene? A and B. Well, how'd you know that? Because they're only worth 1 H, right? And where their frequency's at, right? And they're trans, and you see the 15 coupling constants. Boom and boom. Do you need to know that this is A or this is B? Am I asking you that? No, I'm not. So we can check off A and B, right? We got them done. Got them done. I don't know which one's which, but I know there's 2 protons. One of them is A, one of them is B. It doesn't matter which one is which.
Okay.
I can change my mind later and fix it.
It will matter later.
It will matter later, maybe.
Okay.
But I don't need to make that decision right now. What about this peak at 4.05? That is worth 2 H's, right? So I like to draw a CH, right? And it's split as a quartet. If you're a quartet, how many nearest neighbors do you have?
3.
Right? And it's telling me E is a coupling constant of 7 hertz as well, so that means they're talking to each other. So I can label these C and this one E. But now what's on the other side of this carbon? Now you want to go back and look and say, wait, C is at 4.05. That's pretty D-shielded. What's it probably next to? Or what do I have left that it could be next to? It has to be next to that oxygen, right? Let's just draw that oxygen in there then. Right? I don't know what that oxygen is bonded to. So let's subtract this piece out. So this piece has, minus C2H5O, right? So we have left a CH3. Nice. So I've checked off C and E, and now D is 3 H's and it's a doublet, and all I have left is 3 H's. So I must have a CH3 piece, right? And this must be D. Now, D's at 1.88, right? That should tell you it's a little more D-shielded than you'd expect. What range would that maybe be in? And well, you also know, what else is going on with D?
It's,
There's this coupling constant of 1 hertz. So who's D also talking to? A. So how are we going to put this all together then? So now I have 1, 2, 3, 4 pieces. I want to make D close to A. Right? I want to make D close to one of these protons, right? So that tells you that that CH3 has to be on this alkene. Attached directly, right?
Why is that one B again?
I don't know which one's B yet. I haven't said that. All I know is one of these protons is A, one is B. but I also know that D is talking to one of these protons. So the best way for it to talk to one of these is to be directly attached to it, right?
Only way.
It's the only way, right? It has to get close to talk to it. So so if I have H,
Where is the C double O,
H,
the carbonyl?
I know this CH3, which I'm calling D, which if I'm calling this D, D is talking to who according to coupling constants? D is talking to A. So that means this proton must be, I don't know, we call this one A. Doesn't matter. So now what do I have left to do to put on here? I have how many pieces left?
Okay.
I've used this piece. I've used this piece. I have this piece left and this piece left. So there's only one way I can do it, right? Which is the only way I can do it. I have to put the C double bond O here and put the O, the CH3 over there. Right, it's ugly, I know.
So you were just explaining why you can't do that?
This is the right answer. All right, so back up. Everybody take a step back. Look at it. Look at it again. Look at it again. Right, we know D, according to our numbers, D is talking to A. So that means, and plus of where it's at, 1.88. Look at your table. If you're allylic, right, you're around, right, on your little table, from 1.5 to 2.5. If you're next to a double bond, what frequency will you be at if you're next to a double bond like this? Between 1.5 and 2.5, right? So that makes sense for it to go there by this frequency. It wants to be close to A, right? The other side, there's only, all I have left is this OCH2 CH3 piece and this carbonyl. So there's only one way I can put all this together at this point, right?
So you would never flip the ether with the carbonyl.
I couldn't, because if I put the ether over here, then there's no place for me to attach the carbonyl, right? The carbonyl has two attachment points. The ether just has one, right? So you gotta make sure everybody bonds up, right? You can't make floating pieces around.
Well, what if you switch them around?
You couldn't switch them around, right? You couldn't switch them around on video. So take-home messages. Key things to know. Probably the hardest part about this was seeing that, right, you should see C and E, you should see this quartet and triplet thing, that should be coming out to you and see that a lot now. The key part was 4.05. 4.05 means this HC needs to be next to that oxygen. That was a key thing to see, right? That was the key thing to see, to make it all fall into place.
What would it be at if it wasn't next to the oxygen?
So if you didn't recognize that, and you probably one of the things you could have done was put the CH2, this HC next to the carbonyl, and if it's next to the carbonyl, that's around 2.1, right? And that's all on your table, right? It's all on your table. So that's the key thing to remember, right? It's not just enough to know, right? The coupling, that's great. The number of H's and splitting, but you also got to pay close attention to the frequencies to tell you, right? This CH2 needs to be next to that oxygen. That's the key thing to see. Number 7, exam number 2, 2013. It says, in their IR spectrum, which of these molecules would have a lower frequency for the CO double bond stretch? So we're looking for lower frequency of C double bond O stretch. The two molecules are two molecules, right? Whenever you have these problems, hopefully you guys are starting to recognize this, right? You should start looking for differences, right? What does one molecule have that the other one doesn't have? What can one molecule do that the other can't do? So if I label these A and B, right? They both have C double bond O's. They're both in 5-member rings. They both have pi bonds. All that's the same. What is different? Someone, conjugation, which one's conjugated?
B.
B. So what can B do that A can't do?
Resonance.
Resonance, right? If we can't do resonance, right? To do resonance, can we have an sp3 carbon in the way?
No.
No. Notice, right? This carbon and this carbon are both sp3 hybridized. I can't draw, right? I can't draw this going there. This carbon already has 4 bonds. But I can draw a resonance structure with this. Be careful to balance our charges. Now there's a plus charge over there, right? It might help to number the carbons. 1, 2, 3, 4. 1, 2, 3, 4.
So if we wrote B has more resonance, would that not be,
So let's see what I said. So in the question I say, which of these molecules have a lower frequency for the CO stretch? Explain why using drawings and complete sentences. Which I'm not as big into complete sentences. Because, you know, they're hard for me, so.
The question we had was, don't you have to make a bond when you break a bond?
We did make a
We
bond.
broke 2 bonds and made 1.
So this isn't a, so resonance structures are not reactions.
Okay.
In reactions, you need to make a, if you make a bond, you need to break a bond. Resonance structures are just moving electrons.
Okay.
And
Right.
why can't you do that in A?
Right. Why can't I do that in A? Because A, there's H's here. Right? So I can't move this pi bond there. Right? Because what, I can't kick out, right? Yeah, it'd be there's just no way for me to get, this pi bond's not close enough to this pi bond, right? For it to move the electrons around through a pi system, right? The p orbitals need to be next to each other, right? They need to be fully next to each other, right? So we did the resonance. Okay, so what was the question again, right? What was the question? So which one gives us a lower frequency for C double bond O? So we'd say B, because resonance structure, or just resonance shows single bond character,
And thus,
Todd,
therefore.
ergo, lower frequency. Boom.